Hi everyone, thanks for watching this video. I am going to introduce our work PCAN, Prototypical Cross-Attention Networks for Multiple Object Tracking and Segmentation. PCAN is accepted at NeurIPS as Spotlight Presentation. This is a joint work by researchers from Computer Vision Lab of ETH Zurich, HKUST and KUISHO. Multiple object tracking and segmentation involves tracking and segmenting all objects within a video from a given set of semantic classes, which is an important problem with many real-world applications, including autonomous driving and video analysis. The information encoded in multiple temporal views of an object has the potential of improving the quality of predicted segmentation, localization, and categories. However, effectively and efficiently leveraging the rich temporal information remains a challenging. State-of-the-art methods for MO mainly follow the tracking by detection paradigm, where objects are first detected and segmented in individual frames and then associated over time. Although methods based on the popular tracking by detection philosophy have shown promising results, temporal modeling is limited to the object association phase and only between two adjacent frames. We propose Prototypical Cross-Attention Module for MO. The key component is the efficient prototypical cross-attention operation to retrieve rich temporal information from past frames. PCAN first condenses the spacetime memory and high-resolution frame embeddings into frame-level and instance-level prototypes. The former aims to align an aggregate temporal frame features stored in memory, while the latter one represent each video tracklet with contrastive mixture foreground and background prototypes. It has at least two benefits compared to previous methods. First, it efficiently performs long-term temporal propagation and aggregation. Secondly, it achieves large performance gain on the two largest MO benchmarks with low computation and memory cost. We integrates the frame-level and instance-level modules at two stages in the network. The former aims to align an aggregate temporal frame features stored in memory, while the latter is for propagating the instance appearance features over time and produce instance cross-attention maps to help segmentation. Prototypical cross-attention first produces prototypes by fitting a Gaussian mixtures model to the feature in the memory. We first perform frame-wise clustering for each reference frame to compute the n-key prototypes and the corresponding value embeddings. Then, given the query key encoding of the current frame, we perform prototypical cross-attention to each memory frame independently. The temporal information from different frames are fused as a linear combination, weighted by the feature similarity with the current frame. To further empower our proposed attention mechanism, we utilize the initially detected object mask to identify each foreground instance. We separately model the extracted foreground and background features using a GMM, generating foreground prototypes and background prototypes. The accumulated prototypes for the instance are propagated to the subsequent frames and updated with new appearance prototypes. For each object instance we attend to the foreground and background prototypes separately. The results are concatenated together with the initial mask detection to the temporal segmentation head for final prediction. We randomly select 8 frame prototypes and show their attention distribution on the image. Obviously, each condensed prototype learned to correspond to some semantic concepts of the image covering both the foreground and background areas, such as human, skateboard, umbrella and tennis racket etc. We also perform instance cross-attention maps visualization for the car specified by the red dotted bounding box on BDD dataset. We select the first 4 foreground-background prototypes as example, where each prototype focuses on specific sub-regions of the car with implicit unsupervised temporal consistency over time. These are prototypical instance cross-attention maps visualization for the pedestrian specified by the red dotted bounding box, where the third foreground prototype consistently look at the head part over time while the fourth one attends to the feet region. Here we show the quantitative analysis of PCAN. We experimented PCAN on YouTube-VIS and BDD-MO-S, where PCAN achieves consistent large performance advantages on these two largest MO benchmarks. We perform the ablation study for PCAN on YouTube-VIS dataset, where we study the influence of temporal video length and number of prototypes. The results show the effect of longer-term video information by increasing the temporal memory length. Also, compared to the single prototype representation, by increase the number of instance-level prototypes, GMMs demonstrate a stronger appearance modeling ability. We further find that the performance saturates when the number is larger than 60. Here we show the results on two largest MO benchmarks, BDD and Youtube-VIS. Our main contributions are summarized as follows. First, we introduce the PCAN module for efficiently utilizing long-term spatio-temporal video information. Second, we develop a MO approach that employs PCAN on frame and instance level. Third, we further represent the appearance of each video tracklet with contrastive foreground and background prototypes, which are propagated over time. This is the end of our talk. Scan the QR code for our codes and video resources. Thanks for your watching.